Hello, this is question 8 from the step 2 paper from 2022. We got matrices. We got a matrix here, 2 by 2 matrix, A, B, C, D. It's a real matrix, A is not equal to D. And the transformation represented by M has exactly 2 distinct invariant lines through the origin. Okay. Part 1, show that if neither invariant line is the y-axis, then the gradients of the invariant lines are the roots of that equation there. And then afterwards, we've got the case if one of them is the y-axis. Right, so let's deal with this first case. So if we've got an invariant line, then we're talking about a straight line going through the origin in this case, or 2 straight lines going through the origin, where if we take a point on one of those lines, transform it with matrix M, then we end up back on the same line. Not necessarily the same point, because that would make it an invariant point, but back on the same line. So we've got some line y equals mx because it's going through the origin, and we're taking a point on that line and we're multiplying it by a, b, c, d, transforming it with that matrix. So a point on that line, if it's got x coordinate x, it's going to have y coordinate mx, and that has to get back onto the same line, so maybe to capital X and m times capital X. So we certainly need that to hold, and then hopefully that's going to give us that equation. And we've got then, so ax plus bmx, just multiplying it out, is equal to x, capital X, and then cx plus dmx is equal to m times capital X. So I'll multiply this top one by m, set them equal to each other. So amx plus bm squared x is equal to cx plus dmx. And in this case, we've got the setup where we're not including the option of the y-axis as the invariant line. So here we've got where x is not equal to 0, small x. So I can divide through by that x and get rid of them all, because we don't have to worry about dividing by 0. So what format have they put it in? They just put everything on the left hand side, right? So I've got bm squared plus m times a minus d minus c is 0, which is what we want. So what's going to happen then if we include the y-axis as one of the invariant lines? So in that case, our x-coordinate is going to be 0. So if x is equal to 0, then we've got a, b, c, d, this time multiplied by a 0 for the x value and just some value for y, but that needs to end up back on the y-axis. So let's make that a capital Y. So multiplying this out, I'm going to have that b is equal to 0, because I've got a times 0 plus b times y is equal to 0. So b is equal to 0, and we need the previous equation has got to hold for the other line. Previous equation must hold for the other invariant line. So I've still got this thing is applying, but we've got this case now that b is equal to 0. So therefore we've got that m times a minus d minus c is equal to 0. Okay. So that's figured. Oh, I need what is the gradient of the other, actually. So yeah, I need to actually put m as being c over a minus d on there in order to get the gradient of the other line. Okay, so that's good. That's part 1 done then. So let's get a fresh sheet up. Part 2, show that if the angle between 2 invariant lines is 45 degrees, then we've got this, right? So angle between 2 lines, we're thinking scalar products here, really. So let's sort of jump in on this then. So if we've got theta is 45 degrees, then we've got cos theta is going to be equal to root 2 over 2, which isn't great. That's probably why they got all these squareds kicking around in here, that they've squared that out just to make that a half. So cos squared theta is equal to half. So let's go with squareds in this. I think it's going to make things a lot easier. Right, so what I'm actually dotting here then? I've got these two lines. So what I'm putting stuff into my, a dot b is mod a, mod b, cos theta. But I'm going to square everything so that I've got a half coming out with a cos squared theta. I don't have all these root 2's kicking around. So I've got an a and a b. So my a is going to be, so that's one straight line with, well, I say it's got gradient m1. So I'll say x, m1x. So let's say that's our a. And then for b, I'll say I've got x and m2x. So I've got those dotted together. I want to square those. And then I want to say that's the square of the magnitude of a. So that's going to be x squared plus m1 squared x squared. Should have got rid of these x's before I started, because they're all going to cancel. And then the square of the magnitude of b is x squared plus m2 squared x squared. And then I've got cos squared, which is a half. Yeah, all of these x's are going to go away. So rather than writing the lines as being, say, x m1 x, I should have said, well, okay, that is x times 1 m1, and all those x's are going to cancel. But I'll cancel them now anyway. So when I'm doing this dot, I'll have an x squared and an x squared, which I'll square up to x to the 4, and you can see that's going to cancel with an x to the 4 on the right-hand side. So I'll drop all of the x's in this. So I'm going to get 1 plus m1 m2 squared. That is going to be equal to 1 plus m1 squared times 1 plus m2 squared times a half. So I'll just stick the 2 over there. Right, so that's a nice concise looking equation, but it doesn't have a, b, c's and d's in. So I need to get my connection between m and a, b, c and d, which is here. Well, it's sort of there. It's there for where b is not equal to 0. And then when b was equal to 0, I can't even remember what we had now. That was that m is c over a minus d. So I'm going to need that. So m is c over a minus d. So I've got two cases here depending on what I get for b. But I need this link between my roots. So let's look at the roots. So m1 and m2. So that's just sticking this into the formula. So I've got minus b, so I've got d minus a, plus or minus the square root of a minus d squared, a little more like a d, minus, so plus 4bc, square root, and then I'm dividing by 2b. And I want to have stuff that doesn't have those square roots in, really, because they look horrible. But so if I've got m1, m2, which is sitting here on the left-hand side, is that going to be, that's going to work out quite nicely, isn't it? Because they're going to cancel. I think they're going to cancel, aren't they? They're square roots. So if I do m1 times m2, so I'm going to get the dA over 2b is in both. So I'm going to square that. So I'm going to get d minus a squared over 4b squared. Then I'm going to have the positive square root times the d minus a, and a negative square root times the d minus a. So they're going to cancel. And then I'm going to have minus a minus d squared plus 4bc over 4b squared. That seems quite complicated. Actually, I've got more cancelling here. The d minus a is the same as the a minus d when you square it. So I'm going to be left, they're going to cancel, I'm going to be left with 4bc over 4b squared and a minus sign. So that's minus, the 4's all go away, and I've got a minus, let's just make sure I'm doing this right. So that's cancelling with that. Then that, and that are cancelling, and that is cancelling with that. So I've got a minus c over b. Right, okay, just want to make sure I didn't mess that up. So that's an m1, m2. That looks great. So that's dealt with the left-hand side. On the right-hand side, I've got an m1 squared and an m2 squared. They don't look anywhere near as good because if I square m1, I am going to have the square roots. So I don't like that at all. Is there anything else I can do? Well, if I add m1 and m2, m1 plus m2, that will get rid of the square roots because I've got one of them being plus, the other one being minus. So that'll end up being d minus a over 2b plus d minus a over 2b. So d minus a over b. So that's given me those. So I suppose the question now looks like, can I rewrite this equation with just m1 times m2 and m1 plus m2? So if I can just get rid of everything really easily. So it's the right hand side that's the problem, so I'll have to expand that out. So I don't need a bracket, do I? I've got 1 plus m1 squared plus m2 squared plus m1 m2 squared. No, m1 squared, m2 squared. So that last one's fine because that's just m1 times m2 squared. But I don't want the m1 squared or the m2 squared. So what if I change that to m1 plus m2 all squared minus 2m1 m2? That looks like a good wheeze. Yeah, everything now is just in sums and multiples of m1 and m2. So, right, okay, let's plug it in and see what I get. So I've got 2, 1 plus m1, oh, so minus c over b all squared. That's the left-hand side. Right-hand side, I've got 1, then I've got m1 plus m2. So it's d minus a over b, d minus a over b all squared, minus 2m1 m2. So plus 2c over b. And then I've got an m1 m2 all squared. So plus c squared over b squared. Right. Well, multiplied by b squared. That does seem to be the way to go, doesn't it? So I'd have 2. And what have I got? I've got 2, so I can put a b there. Minus c squared is b squared plus d minus a squared plus 2cb plus c squared. I've got a lot of things now that are in the answer. So I've got the left-hand side. This right-hand side, that's a b plus c squared. That's not going to help, is it? Having a b plus c all squared. Doesn't get me, I think I've got to expand out again. So I'd have 2b squared plus 2c squared minus 4bc is that. So let's get rid of b squared on both sides, c squared on both sides. This is looking good. And then take off another 2bc. And that is equal to, well, let's get it as an a minus d squared, like they've written in the question. So, oh yeah, I'm there. Right, I am there. Because I have now got a b minus c squared minus 4bc. Yes, okay, so we're there. Oof. Okay, right. So I suppose the trick in this one was seeing that we had to rewrite this. That the combinations of roots that we wanted were multiplying them and adding them. We didn't want to square them. And then getting rid of these m1 squareds and m2 squareds. So that's the step in this particular question. Except I've only done that for b is not equal to 0, haven't I? I haven't done it for b is equal to 0. So if b is equal to 0, I've now got, so we're coming back up to this point. So this is for b is not equal to 0. So that's b is not equal to 0. And then here then, so if I've got b is equal to 0, one of my lines, let's do the simplified version of the lines without the x's in. So I'm going to have 0, 1 is my y-axis. And then I've got this gradient. All right, so that's immediately dropped in with what I want. So I'm going to have a 1 and a c over a minus d. So I don't have to do, and I'm squaring all of that. I don't have to do all this messing around with the roots because I've got one obvious root. That is equal to square of the magnitude of this one, which is just 1, and then the square of the magnitude of that one, so that's going to be 1 plus c squared over a minus d all squared, multiplied by a half. Okay, right, so I'm in a similar sort of position here. So what am I getting when I do this dot product then? I'm running out of space on all of this. I'm getting c squared, and let's multiply by the 2. So 2c squared over a minus d all squared is equal to 1 plus c squared over a minus d all squared. Okay, right, so I can cancel that from both sides and say that c squared is a minus d all squared. So c squared equals a minus d all squared. Right, so that wasn't as bad then for the case when we've got b is equal to 0. In fact, it's exactly the same. I wonder if I could have got away with just putting, if b of 0 in there, I get c squared is equal to a minus d squared. So yeah, consistency, whether I would have been justified in saying that, I'm not really too sure, but still, at least it's consistent between the two answers, which is always a pleasing thing to see. So right, so I'm on to what, part 3. So new sheet. What am I doing now? Find a necessary and sufficient condition. Okay. I'm wondering why. Okay, they've specified necessary and sufficient, but I'll worry about that at the end. On some or all of A, B, C, and D, there are two invariant lines that make equal angles with the line y equals x. Right, okay, that doesn't sound too bad. That's kind of similar to what we've just done, because we'll be saying then that if we've got one line which is 1, m1, and I dot that with 1, 1, which is the y equals x line, and they've got to make the same angle, so I've got to divide by the magnitudes of each one of these. So the magnitudes, should I go with a whole squared thing again? Yeah, let's go with a squared thing again. So I'm going to square that because I don't have to worry about the square roots on the bottom. So I'm going to get the magnitude of this one is 1 plus m1 squared, and the magnitude of that one is 2 squared anyway, when I've squared it all. So I've got that. Now for the other one, well, it's just going to be the same, but writing an m2 in there. So that dotted with 1, 1, square it all is equal to 1 plus m2 squared times 2. Right, so I can get rid of the 2's. That's great. And I'm going to be cross multiplying a lot of things here. So I'm going to have 1 plus m1 squared times 1 plus m2 squared, but the squareds are in a different place, even though I said it in the same way, is going to be 1 plus m2 all squared times 1 plus m1 squared. Right, so I've got that. I suppose I've just got to expand out and see what cancels, I suppose. So I've got 1 plus, well, I'm going to have one lot of all this expanded. So it's 1 plus m1 squared plus 2m1. And then I've got it all again multiplied by m2 squared. So plus m2 squared plus m1 squared m2 squared plus 2m1 m2 squared. So that's the left-hand side. And then that has got to be equal to exactly the same thing, but I swap over the 1's and the 2's. So 1 plus m2 squared plus 2m2 plus m1 squared plus m1 squared m2 squared plus 2m2 m1 squared. So let's do some cancelling. The 1's go, the m2 squareds go, the m1 squareds go, the other things don't. Oh no, that goes and that goes. So I'm left with 2m1. I can get rid of all these 2's as well. Let's get rid of more 2's. So 2, 2, 2, 2. And I've got an m1 plus m1 m2 squared minus m2 minus m2 m1 squared equals 0. Right, so what am I going to be able to do with that? I mean, that's got, yeah, I've got factorising I can do on this, haven't I? I've got an m1 minus m2. What am I going to factorise? How am I going to go about it? I could say I've got an m1 minus m2. That's certainly going to end up being a feature of this. And then I've got an m1 m2 times m2 minus m1. equals 0. So that is m1 minus m2 plus, so that's a negative of that. So not plus, multiplied by, factorising. So that's going to be, I've got a negative of this. So 1 to get that one, and then a minus m1, m2 to get the other one is equal to 0. Right, find a necessary and sufficient condition on some or all of A, B, C, D, two invariant lines to make equal angles. Right, so what does that mean? What does that mean? Because again, I haven't got A, B, C's, D's in here, but I do have relationships between these things. The two invariant lines, so I've got two different lines. So M1's not equal to M2. So I've got that M1, M2 is equal to 1. And M1, M2 was equal to something. M1, M2 is minus C over B. So that's minus C over B. Okay, so I've got that C is equal to minus B is what I need on that for the necessary and sufficient condition for those. But that is the case of B not being equal to 0. So I've got to do it again, haven't I? I've got to go back in and say, find the necessary for the two to make equal angles. So if I've got the y-axis, I've got the x-axis as well. So, oh yeah, that's going to be a quicker option then. So if B, this is for B is not equal to 0. So if B is equal to 0, then we're saying that the x-axis is also invariant. That's going to save me a bit of working out, isn't it? Because they've got to be equal angles from y equals x. So if we've got the y-axis, we must have the x-axis to make them equal angles. So A, B, C, D times x0 has got to go to x0. So that means that C has got to be equal to 0. That's exactly the same as we had in part 1 when we were working through. So to get that 0 there for y, we've got C times x. So C must be 0. So we've got that. That's probably it, really, isn't it? I mean, that's the same as what we did in part 1 for that bit. So yeah, so that's two conditions. Find it necessary and sufficient. I wonder why they've written it that way. It's necessary and sufficient. So if we've got the lines are an equal angle away from that, then it's saying we must have this thing apply. Okay, well, it does, but it could be that we've got a different solution. I mean, maybe that's what they're just trying to cut down the requirements, that we don't need to show there's some other condition that can cause that relationship between the lines and the angle. As in, if we've got this, and I'm not certain this is right, but the way I'm reading that requirement on necessary and sufficient is that, okay, if we've got this relationship between B and C, then we will have these two invariant lines making equal angles with y equals x. But there may be other conditions, other relationships between A, B, C, and D that also produce that same equal angle outcome. But it's not incumbent on us in order to find what those might be. We've just found something here, which is right. Well, that's sufficient to say that we've got an answer. There might be other answers. I mean, maybe that's what they're getting at. I'm not certain on that. So if you've got a better idea, let me know. But I think that might be what they're getting at. Anyway, at least I've found these two conditions. We've got C is equal to minus B if B is not equal to 0, and then C is 0. Actually, it ends up being the same condition, doesn't it? Because if C is 0 when B is 0, it still fits with this. So all we really need is that. And then we're okay in both cases. So maybe worth putting a note of that as per C is equal to minus B. Right, so last bit then, part 4. Give an example of a matrix which satisfies both the conditions. All right, that should be pretty easy then. That's it, I need a new sheet for that. So we need something which has got, so it's satisfying C is equal to minus B. So let's say we got a 1 and a minus 1. Let's go with that. And then I need also to satisfy this thing. So if C is minus B, I've got here that that's going to be 4b squared. Let's go with b squared. And then that will be plus another 4b squared. So I've got 8b squared. A minus D, let's just make D equal to 0. And then so A squared would be 8b squared. So it's going to have to be 2 root 2 times b. So 2 root 2 will do. I mean, you could have anything that fits in with that. It's going to be fine. So, okay, that was an easy finish to the question. Yeah, that was a fun question. I like that. I suppose the only thing that's slightly hanging is that they put necessary and sufficient there. Because usually with the necessary and sufficient ones, I say usually, quite often, I mean, maybe it's usually as well, but quite often with those, it's just saying, okay, I've worked out here going from top to bottom. And then say, well, you would have got the same thing if you worked in the other direction. Because that's then setting up that if we've got P, then we've got Q. If P, then Q. So if we've got Q, we must end up having P. So it means you can work in both directions. So maybe that's all it is, that if we had started from this position of C equals minus B, then we inevitably get the input that we wanted. So that could be, that's the sort of thing we go for. But maybe they're just trying to rule out the possibility of other solutions and really, taking that stress off of us when we're coming up with an answer. But I really like that question. I thought that was a fun one. Yeah, quite pleasing. You never know what you're going to get with a matrix one. Sometimes matrices questions can be really unpleasant, but that one seemed quite nice. So there you go. It's question 8 done.